Okay, so this is sort of the research video. Since this is a separate video, can you remind the audience who you are?
Yeah, hi. I am Robert Dix. I am a third year math PhD student at the University of Illinois at Urbana-Champaign. I do research in number theory, and much of my research has to do with modular forms.
Nice. So as of now, with like recent stuff that you've been doing, what are the kind of broad themes that your research does with these modular forms in number theory?
Yeah, so right now my research is a little bit narrow,
Mhm.
but I will just say that I study Q expansion coefficients for certain spaces of modular forms. And you could also say that this often involves studying arithmetic properties of these coefficients. Yeah, so just as a quick reminder, I'll just say modular forms. When I say Q expansion, I mean the following thing. Modular forms have a power series expansion where Q is e to the 2 pi I z. And for me, most of the time, and it's going to go from 0 to infinity.
Nice. How does this theme relate to things that you may be currently researching?
Oh, well, after finishing my second paper, I haven't really done that much research at the moment.
Uh-huh.
There's something I did 2 years ago, which is exactly, it's very, I guess, it gets your hands dirty, so to speak, with these coefficients and studying some very technical specific properties related to them.
Hmm.
So in some sense, this is exactly what I'm doing in terms of writing up some of the things I did 2 years ago.
Nice.
Yeah.
Nice, nice, nice. And what has your previous research been like?
Well, if I wanted to give a tongue-in-cheek answer, I would say like really, really nice. And who knew that being a math PhD student led to a stress-free life? But let's see. So there have been some challenges. One thing that's often discussed when you're talking about graduate students, there is a transition period between when you're just a student who's just doing problem sets. You have to, turn this in on Wednesday, and you have to do these 5 problems from this textbook, and you have to go to the lectures and review the lecture notes, and go to office hours. Just being a student essentially. And then
Uh-huh.
there's kind of the real world, going out into the wild, so to speak, and proving theorems that haven't been proven before.
Hmm.
So that transition can be very daunting in a lot of ways. And it's hard to kind of, when you're starting out, as I did essentially last year. I did some undergraduate research, but I don't talk about that. When I was starting out in my graduate research,
Uh-huh.
it can be definitely very intimidating to kind of approach something that hasn't yet been proven before, especially when you're just a wee little young boy who needs to develop his own reputation, so to speak. Um,
Yeah.
but after a certain point in time, you just kind of have to find what works for you, and developing a sort of rhythm and how you just kind of read papers and be able to. Sometimes it's good to have other things going on mathematically or otherwise to not focus too much on one thing, I guess. So it's been very nice in a lot of ways, but definitely I felt the weight of that burden of I am now trying to prove something that's never been proven before, as far as we know, and that can be very intimidating. But after a while, you kind of get used to it.
Yeah. What kind of non-mathy stuff do you like to do just to sort of lighten the mental load?
So I do like to exercise a lot, and so in 2019, I did run a marathon. In like the most
Nice.
silly way possible. Like I just like ran a lot. I didn't even look up anything, didn't look up nutrition, what I should like I don't know, drink on marathon day or
Uh-huh.
like I didn't do any of that. I just ran a lot and decided to run a marathon. So I do like exercise a lot.
Mhm.
And I just set for myself kind of these kind of weird challenges. Like for instance, I had the brilliant idea of like doing 1,000 burpees in a day, just trying to, and I did it. And I've actually done that more than I should have. But I just set these like weird challenges. For instance, I like chess a lot. To go to a different topic, I
Uh-huh.
like chess. I played the clarinet, and I have played the clarinet now for what is going to be like 15. No, it should be more than 15 years now, because I started in 2005, so definitely more than 15 years. That's a big thing for me as well. Um, so those are some things that kind of keep me going, so to speak. And I'm also a devout Christian, so I do various things with my church as well.
Uh-huh.
Yeah, I lead a Bible study in particular that meets on Saturday. So in particular, met today. So that can help me kind of get out of a mathy mode.
Nice. Just for the runners of the audience, what was your marathon time?
Oh, okay. So it was 5 hours. Like that's
Uh-huh.
not fast. For those who know about marathons, yes, it's not fast at all. But as I said, I didn't look up
Yeah,
anything. I I just did
exactly. You finished.
it. Yeah.
That's still amazing. Congrats on that.
Thanks.
Um, you're welcome. So now to move on to the more mathy things. We got the non-mathy stuff down. Um, let's talk a bit about your most recently published paper, which is the higher weight Og's theorem, correct?
Oh yeah, published. Okay, yes. Uh-huh.
Yeah. So just to sort of like get a general sense, what kind of stuff did you do in that paper?
So there's a theorem of Og that is a very geometric theorem, and it has to do with properties of modular curves. And so I'm going to write down something about this. The modular curve x0 of n. So I mentioned that you can, in the previous video,
Uh-huh.
that you can construct modular curves using congruent subgroups that aren't SL2Z, like so smaller subgroups of SL2Z. X0 of
Yeah.
n is one such modular curve. I'll prove that if P divides, P is a prime, divides n exactly once,
Uh-huh.
then infinity is not a Weierstrass point. On x0 of n if the genus of x0 n over p is 0. So I've said some things about some terminology, so I should probably say a word about what this means. So
Mhm.
the way to think about genus is like you can think of it as just the number of holes. So if I take a sphere, it's genus 0. It has no holes.
Yeah.
And if you take like a donut, it has genus 1. It has one hole. Whatever that means. There's always technical ways of making sense of what I mean by hole, but just from a colloquial standpoint, that's what it means. As far as infinity, oftentimes, we think of infinity as in a sort of complicated way. Let's just say it's a special point on this modular curve, which we can call the point at infinity, but it's not as special as it sounds, let's just say.
Mhm.
So it's just some special point on this modular curve, which somehow deserves the title of infinity, but it's not the usual notion where we're just thinking about, going out into infinity. This is the cusp infinity. So it's a special point on the modular curve that's called infinity for technical reasons. What is a Weierstrass point? Well, I'm going to just say that for my research, I actually didn't really need to know what a Weierstrass point was.
Uh-huh.
And the reason was that I just used an equivalent condition, which I could translate this notion of being a Weierstrass point in terms of weight 2 modular forms and some conditional weight 2 modular forms. But if I were to give a definition, or to kind of give some sense of what the definition is, it has to do with special functions on this modular curve. So something I didn't say before is that modular curves are Riemann surfaces,
Uh-huh.
which you can think of as just geometric objects that when you zoom in on a point, like really, really closely, it looks like the complex plane. Okay,
Uh-huh.
and they have dimension one. Okay, so to give an example of with in terms of the real plane, I'll just kind of give this example of a sphere. If you were to take this point and just zoom in really, really closely, this looks like a normal coordinate plane, you know, in 2 dimensions.
Uh-huh.
But of course, for some things, you have to zoom in very, very close. So it's a very similar notion. That's a Riemann surface as far as we're concerned.
Uh-huh.
And you say a point is a Weierstrass point, or if there does not exist, okay, certain functions that have poles of certain orders. So I need to
Mm-hmm.
tell you what a pole is.
Yeah.
So this is not like a voting pole. In some sense, it's the opposite of a zero. So what do I mean by zero? It's exactly what you think it is. So if I take, I'll just kind of be on this part,
Uh-huh.
just thinking about what a pole is. You take a function g on something, whatever this is, x, some space,
Uh-huh.
that's like a Riemann surface or whatever. And well, no, I'll just work with c and just say there's a similar notion for Riemann surfaces.
Uh-huh.
Okay, you say g has a zero. Or actually, I'm going to make this a polynomial. I'm just going to make things as easy as possible because, why not?
Yeah, exactly.
So this is a polynomial. It's exactly what you think it is. G of z equals x minus z to the m, h of z for some other polynomial. This implies that z is a zero of order m. As I'm saying this, I realize I probably actually didn't need to point this out, but let's just say you can think of a pole as an opposite of a zero. So
Uh-huh.
I'll give an example. So to give an example, if I take 1 over x minus z, then z is a pole of order 1. I'll just say that.
Uh-huh.
And if I have 1 over x minus z to the m, it's a pole of order m.
Uh-huh.
So Weierstrass points are points where you can have a function with a pole of an order you don't expect. So
Uh-huh.
for most points, you're not going to have functions that have poles of certain orders, but sometimes you do. So at such points, those are Weierstrass points as far as we're concerned. It has to do
Uh-huh.
with having poles of certain orders that you don't expect.
Yeah.
Yeah, so I proved some sort of generalization in a suitable sense of this kind of theorem, but I kind of got kind of in the nitty gritty in terms of modular forms. I didn't really consider geometry at all.
Okay. So why did you choose to specifically go to Ogg's theorem?
Oh, yeah, this one has a really short answer. My advisor said this might be a good idea.
Uh-huh.
Yeah.
Yeah, that's really nice. So you said like you were able to just say, we don't want geometry, we can just do modular forms. How did that work? Like, how did the proof of your main theorem kind of go with that?
Oh, well, this is kind of a humbling experience. So sometimes when you start out with doing research, it can be hard to let yourself be human. So what do I mean by that? It means that when you have this whole mountain of things that you want to do, and you want to do research that is like groundbreaking and breathtaking and original, and when you're a beginning graduate student or fairly early on in your program, you just can't do that. You have to work on something that's a lot smaller.
Uh-huh.
So with this, there was a paper of, well, I'll just say Algren, Masri, and Rouse. And my advisor is Scott Algren, and who's a number theorist at Urban Champaign, which essentially gave a certain formula which allowed me in particular to translate this information in terms of modular forms. And so much of what I did for that paper, basically take this formula and try to understand every single aspect that I could. And if you were to search the title, I believe, is Vanishing of Modular Forms at Infinity. If you were to search this, you would surely this paper would come up. It's a paper from like 2008 or something like that. And in particular, it's the result I used was theorem 4.2 in that paper. So it kind of gave a certain formula which turned out to be extremely useful for me. And so much of why I was able to do this was because I was able to understand this formula basically as much as I possibly could. In terms of technical details, theorem 4.2 of that paper will be able to explain some of that.
Yeah. What did that formula tell you?
Oh, that's a great question. So it is kind of technical and complicated. But one thing I will tell you is the following, actually. So I'm going to go back to talking about expansions, because this is basically what I do for my research. So when you take a modular form, it has an expansion that looks like this. Okay. And so you can have the notion of the order of vanishing at infinity. And so what is this? The order of vanishing at infinity is exactly where this expansion starts. It's the first non-zero coefficient. Okay, so if I had a modular form, imagine that I had a modular form that starts with q plus blah, 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 then the order of vanishing is exactly 1, because first non-zero exponent. So the first exponent for which there is a non-zero coefficient, so the order of vanishing is 1 because the first exponent is 1. Okay. So this formula allows one to bound, to give an inequality, so to speak, for the order of vanishing for certain spaces of modular forms. So it's some long, complicated thing, but for each modular form in a certain space, you can say order of vanishing is less than or equal to blah, blah, blah.
And that allowed you to do everything you wanted through that paper?
Yeah, essentially, well, except for one little thing at the end, essentially, yes.
And what was that little thing?
Yes. What is that little thing? Okay. So now I need to think about something slightly different. So I'll just kind of backtrack and say, I proved some theorem that says F, a Cus form, actually, satisfying blah, blah, blah. Or I'll just say blah, blah. It's very important to only have 2 blahs.
Yeah.
So means order of vanishing is less than or equal to blah, blah, blah.
Mm-hmm.
So I'm using this because it's kind of long, so I added an extra blah to reflect that. And so I wanted to think about modular forms or Cus forms. So I'll just write this down. I wanted to think about Cus forms for which the order of vanishing at infinity of F was actually greater than the thing I said it would be less than. But of course, I'm omitting some technical conditions, because my theorem is F satisfies blah, 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 or blah, blah, means that order of vanishing is less than blah, blah, blah. But I also wanted to think about forms which don't necessarily satisfy condition blah, blah. And think about, is there some way I can understand, is there some way for me to understand these forms that are greater than the bound I said that these forms should have? Okay. So I wanted to understand, just to summarize, forms for which the bound did not hold. And so I was actually able to do this. And so I'll need a new whiteboard. If I write WKPN, we're not going to worry about why exactly I'm writing this, but let's just say n is a positive integer and p is a prime. I was able to study the dimension of this. So it turns out this thing is a vector space. I can look at the dimension of this, and I can actually say that this is less than or equal to the dimension of this space of cusp-forms, where I haven't actually said what exactly this is. So this last little bit, it's funny. It's a very small piece of the paper. It's actually the most interesting part. And there's kind of a story that goes along with it, because my advisor expected that something of this shape should be true, but he gave me some way of proving it. In his mind, he had like, oh, well, the proof or a proof should probably proceed along these sorts of lines. And he gave me something that was kind of something I just didn't really understand at all. And so I just took some time and I tried to kind of understand what he was getting at, and I couldn't do it. So I thought to myself, you know what? I'm just going to do something different. I didn't know what that was. I just decided to strike out my own path. And one day while I was exercising, or one night rather, I just kind of had this flash. I had this book, which I mentioned before in the previous video that's next to me. And I read something from it, I guess some days prior, that might be relevant, but I didn't exactly know how. But it just kind of came in a flash that something from that book might actually ease my burden in a way that I could apply a theorem from linear algebra to actually get a handle on this dimension. And it was very short and very elegant, and it just came in a flash, so to speak. It was like gifted to me after working hard, I guess.
Yay.
So it was a really cool moment. Just kind of like my first like insight.
What did you use from linear algebra? And like how, since it was like such a simple theorem, do you think you would be able to explain what was going on at that sort of like level?
Well, I could give you the theorem from linear algebra, certainly, and then we can see what happens from there. Okay,
Yeah.
so for those who know something about linear algebra, this is the rank nullity theorem. And I just said it's a very simple theorem, and I sure hope I don't state it incorrectly. So imagine in this universe that V and W are vector spaces. And T from V to W is a linear transformation. Okay, so it turns out that you have the following formula. You have the dimension of V, I hope I get this right, is equal to the nullity of T plus the rank of T. Okay, I believe this is correct. Okay. I just graded for linear algebra, so surely I should know. Okay, but yes.
Exactly.
So this is it. This is what I used, and I'm just gonna kind of summarize where it comes up. So there is a certain operator or a certain linear operator. I'll just call it T for now. Might as well. From cusp forms, and I'll just say of level Pn. I didn't really say much about what exactly I mean by that, but we're not going to worry about it right now. To cusp forms of level N, it turns out to be surjective. So this turns out to be surjective. And because it's surjective, that means, of course, having full rank. And so I was able to use this to say the following, that the dimension of where I started is equal to the dimension of the null space, which I'll abbreviate as, I don't think I've ever seen it abbreviated like this, but it's okay. There are no rules. Plus the dimension of SKN. And I'll just say that modular forms naturally live in finite dimensional vector spaces, so all the stuff I'm writing makes sense. Okay, so it turns out the thing I wanted was this. So I just subtract off one thing. I just subtract off this from both sides, and I have exactly what I need.
Is the WKPN, is that sort of related to the null space of what we're looking for?
Oh, yes. Okay. So now, yes, this operator, I'm going to actually write it like this because it's actually the trace operator. And so this dimension of WKPN is somehow related to the dimension of the null space of trace, which is another word for null space is kernel, which is, I'm going to write it because it's more familiar to me.
Uh-huh.
The kernel of the trace, well, trace always comes with, when we're dealing in this way, with respect to the level. So I'm just going to adorn it like so.
Hmm.
So these are related in some way, that if I'm being honest, for the moment, I don't quite remember. Uh,
Uh-huh.
but they are indeed related in some way. They are related in some way. They are related. They're related. Okay. I
Yeah.
have
And
to.
in your research, you did that, and that this sort of connection is what helped you do this like a really cool small bit at the end. That was the most elegant part of it.
Yeah. It was, and ooh, okay. Yeah, I would have to think about exactly where it comes in. Yeah.
Yeah. And so with this paper, the main thing that you proved wasn't exactly the generalization of Ogg's theorem. Ogg's theorem came as a corollary from that. What made you want to go with the big theorem instead of just attacking Ogg's theorem right at the get?
Oh, just to clarify, the big theorem really is the generalization to higher weights. So Ogg's theorem itself was actually reproven using methods very similar to what I used in the Algren-Masri-Rouse paper. So that's one
Uh-huh.
reason I didn't quite go for it, because Algren, Masri, and Rouse had already did it, and I wanted to see what happens for weights that are larger than 2.
Hmm.
So it's a generalization with respect to the following thing I haven't discussed yet. So I talked about Weierstrass points. You can actually translate the condition of infinity not being a Weierstrass point in terms of weight 2 modular forms. And this is exactly how Algren, Masri, and Rouse reproved Ogg's theorem using these
Uh-huh.
modular forms. And so what I did was just say, oh, hey, this weight k is 2 in this, reformulated version. What happens when the weight is k?
Hmm. What complexities arose because of that? Like what things couldn't you use for weight two that you had to like sort of slide around for higher weights?
Well, if I were to give a tongue-in-cheek answer, it would be kind of
Hmm.
nothing. But the thing that I would say is that it turns out that a lot of the tools, to be more, I guess, precise, a lot of the tools that were useful for reproving Ogg's theorem in the weight 2 case could just be amended in some sort of natural way to actually be able to help you handle higher weights. In some sense,
Hmm.
what my theorem showed is that the 2 didn't actually matter. That a lot of the things you did in weight 2 actually just generalize in a natural way, but you have to make a few adjustments that are not
Uh-huh.
particularly difficult.
So you just like took like you guys don't have to worry about weight two. We can do this for literally any weight you guys care about.
Exactly.
Nice.
Using very similar tools.
That's really cool. And also throughout this paper, there was for like a lot of the major stipulations, I was that P should not divide N. What sort of goes wrong if you have P dividing N?
I guess I would just say I am not entirely sure of why the technical conditions in Ogg's original theorem, let's just say, were the way they were. I imagine it has to do with something technical related to the geometry of modular curves.
Hmm.
Yeah.
But yeah, you like your coefficients. We don't got to worry about that other bit.
Yeah, right now it's just something that I know there's some very high level geometric reason that sometimes you don't want p dividing n, or you want p dividing n exactly once,
Uh-huh.
um, and I just don't know that yet.
Sweet. And then this is sort of like more of a broad question, but do you remember sort of what the process of writing it was like?
Oh, oh yes I do. So yes, it was a wonderful day in March of 2020, um,
Uh-huh.
and I tend to work at night, and so it was a night, and I had been looking at this formula that I mentioned before, this thing where I said order of vanishing is less than blah blah blah, and I had been looking at that for some weeks, and had been dealing with some like special cases. So I started out by proving things for weight 4 and weight 6 before I started looking at general K.
Uh-huh.
And so I realized that I actually didn't understand something completely. I had been thinking about the formula entirely incorrectly. And when I had that particular insight, I decided that I was going to see if I could work out all the details of what I previously thought would go wrong actually turned out to not go wrong at all. So I thought, what if I tried to work out the details in the same way that I worked out for weights 4 and 6 and see what happens?
Uh-huh.
So one very, very long night, I actually proved this main theorem, this theorem probably 1.2 in the paper.
Hmm.
I actually proved it all, that night, that same night that I understood that I hadn't been thinking about the formula correctly. And once I understood the way in which I had been thinking incorrectly, I could just go full steam ahead and work out all the details and see if I hit any other roadblocks. And it turns out I
Hmm.
didn't. So that was a wonderful night.
Can you speak to sort of what you were having trouble understanding, and then what you sort of understood throughout that night?
Um, I really wish I could.
Uh-huh.
so,
Yeah.
so I don't think I'll be able to give I'll just say that it is quite technical, and I don't think I'll be able to explain in a short time
Yeah.
exactly what it was. And I think that now that everything's written cleanly, I'm not even sure I really remember exactly what it was. It's like it's often what happens in math, where it's like you're at a place where you don't understand anything, and everything is just like a giant cloud of concepts. Then you understand
Uh-huh.
everything, and then you can't remember what it was like not to understand. So I think it's a very similar thing where I'm not sure I even remember what it was.
Yeah. That's good to know. You're just like, I always understood it. Never didn't
Good
understand it.
feeling. Like now that it's kind of written down, and of course, there was something obviously that I have to look back at as we've looked at here
Uh-huh.
with the WKPN. But once I do that, like it won't like I could just remember exactly what was going on just very easily. I just need to take a second look.
Nice. When you were doing this paper, what would you say is like the most important thing that you learned and like your undergrad, your grad, something you like consulted with your advisor with, that like was like, I use this thing and that's how I understood how to do this paper?
Oh, rank melody. If I were being honest, fully
Uh-huh.
honest. In terms, but that's for the last part. For the other parts, there's a lot of like finicky manipulating with modular arithmetic. So I would say
Hmm.
that just my general sort of number theory, I guess, courses or my understanding of, I guess, modular arithmetic did come in a very crucial way with some of these specific formulas. Certainly number theory in that sense, in the elementary number theory sense, came in. As far as other things, I think having like comfort with working with Fourier expansions, even though it doesn't, there's no technical like analysis that involves knowing what a Fourier expansion is fully, but I think
Uh-huh.
just having that sort of psychological comfort that I know what this is, even if I'm not using it, because that can also be very daunting. If I were to read a math paper and then they mention like, oh, we use stacks, it's like, okay, what's a stack? That'll be
Uh-huh.
the first question. It may not be important to know what a stack is to like understand the rest of the paper, but at the same time, it's like if I'm reading this and I don't know what a stack is, like psychologically, that's very, very daunting. So
Uh-huh.
I'm much more comfortable with like what Fourier expansions are just from my analysis courses. And so my ability to work with them is definitely heightened by that comfort. Um,
Nice. Thank you so much.